In this lesson, we cover some specific details about chemical equilibrium, the law of mass action, and the equilibrium constant. Now, a few details before you spend much time on here. There are a few things that we assume that you have already been introduced to. We assume that you already are familiar with the idea of a reversible reaction, that you know what an equilibrium is, a dynamic equilibrium in which reactions are occurring in both directions to produce no net change in concentration amounts in products or reactants. And you should have also had a little bit of a qualitative introduction to Le Chatelier's principle. And for my class, you should also have some experience with the reactions running to constancy, such as in the beans activity that I used to illustrate this idea. So here's a link to a useful simulation, which we don't really we're not necessarily going to use this a lot in this lesson, although it is generally very helpful if you wish to understand why some of these things that we're about to talk about behave the way that they do. Consider this reaction. We have some generic chemical species A, B, C, and D that are in a reversible reaction. And if you notice here, you'll see that all of these have little AQ indicating that they are aqueous species. So what that means is that these are quantified by their concentrations, and therefore we can think of them through the collision model. The collision model being the model used in that simulation I just linked, where you can kind of watch all of the different atoms and molecules bouncing around and reacting with each other based on their collisions. This is also, by the way, possible to do with gaseous substances, but not solids and liquids. As we have learned, this reaction, this reversible reaction, will reach an equilibrium in which the overall concentrations don't change anymore, and in that hypothetical scenario, we could then go through and we could determine the concentration for each of the four species. If we wanted to, then we could use those concentrations to write an equation expressing the products of the products, that would be C times D, divided by the product of the reactants, A times B. And if we did that, it would look something like this: C times D divided by A times B, again, the products divided by the reactants. The law of mass action says that this ratio of products to reactants will always be constant for this reaction at a given temperature. If the temperature is changed, if you run it at a higher or lower temperature, that can change the value of this number that you get. But at the same temperature, you would always get the same value by measuring these concentrations of the four species and plugging them into this formula. And therefore we call that the equilibrium constant. That number that you generate in this way is called the equilibrium constant, and it's symbolized by KEQ. So yeah, I guess I needed to push through those slides there so you can write that down. So the equilibrium constant, it's the same. It's always the same for a given reaction at a given temperature. It is known for all important reactions, often be given at the beginning of a problem. You can look them up in a book, and can also be written as an expression once you know the reaction is known. So it's a number, but it's also expression, and the expression will produce that number. So here's how you write an equilibrium expression. It's a little bit more complicated than what I've shown so far. Let's take this following reaction, the ammonia synthesis reaction. Note, of course, that these are all gases, all got little g's. Gases can be measured by their concentrations or by their partial pressures. It doesn't really matter which. That will change the value of K. We'll get into that in just a little bit. So we have these gases. If we calculate these values, we've been talking about concentrations, but we could just as easily measure their partial pressures and plug those into the formula to get our K. And if we do that, if we use partial pressures, of ammonia, hydrogen, and nitrogen to generate our equilibrium constant, then it would be labeled Kp, the P being for pressure. If we were to measure them as molarities, which we could do for gases, it's not common, but we could do that, then we would label it Kc. For most aqueous solution reactions, which are quite common, we will use molarities, and this would be the label we would give it, Kc, C for concentration. So again, Kc and Kp both work exactly the same way. They're not really different things, they're different labels, but their values, the number you generate with them, will not be the same. They are, however, convertible into one another. We're not going to get through how to do that right now. It's not what we're concerned with right now, but it is possible to convert a Kc into a Kp and vice versa. So back to our reaction. So if you have K, you can label just KEQ, if you're not worried about whether it's a Kp or a Kc. KEQ is our general label for the equilibrium constant. So let's calculate, let's say that we were using partial pressures for this reaction. Let's calculate the Kp here. We're not going to actually get the number. We're not going to work with numbers, but we're going to generate an expression. How would you get the expression? Well, we would, again, products over the reactants. So we would take the partial pressure of ammonia, plug that in there, and then put that on the top. And then the reactants would go on the bottom. We'd take our nitrogen partial pressure times our hydrogen partial pressure, and that would generate a Kp of NH3 divided by the product of N2 times H2. But there is a little bit more than that to it. Coefficients in the reaction equation alter the equilibrium constant calculation. They turn into exponents in the expression. So here we do have some coefficients. We have a coefficient of 3, and of 2, and of 1. So they turn into exponents in the appropriate place in the equation. So our NH3, which is expressed here, is going to get an exponent of 2. We're going to get that 3 down onto the H2 as an exponent. And since there is not a coefficient on the N, it just stays like that. And so that is our actual equilibrium expression for Kp for the ammonia production. NH3 squared over the product of N2 times H2 cubed. And these, again, are partial pressures that we would be plugging in for these values in the brackets. A bracket like that, the brackets around here, these mean that you're going to take the molarity of, or the partial pressure of, those values. So now you try it. Write an expression for the following reaction. Here's the reaction, and I'm going to reveal the answer in just a second. So if you want to try it yourself, now is when you should pause the video. Alright, so this is what we should be getting. We should get a value of that, which you can look at in a little more detail if you want to later. Now there's one other thing, a really important thing to mention here before we move on. I have left something out. This is not a minor detail. It deserves its own entire lesson, but we don't have time for it right here. So for reasons that we will discuss later, equilibrium constant expressions always must ignore any substance that is in a solid or a liquid state. We only use aqueous and gaseous substances. Remember what we were saying earlier about the collision model? The solids and the liquids, they don't really behave in the same way that aqueous or gas substances do in the collision model, and also their concentrations don't really change if you're solid or liquid. So there's a lot more we could get into that, and will later. So whenever we have something like this, an equilibrium with mixed states, we have solids and liquids and gases, and we call that a heterogeneous equilibrium. I have it pluralized here, equilibria. And whenever we do that, we ignore, when we're writing the expression, we ignore any solids and liquids. So here's an example. If we're going to write this expression, we would have the product CO2 times CaO over CaCO3. However, you notice that the calcium carbonate here and the calcium oxide here are both solid, so they would be ignored. So you would write the exact same expression, and you would just completely leave out those parts. And so your equilibrium constant would just be the concentration of CO2.